After finishing that quiz, you may have some idea. For this placing ball module, it seems that our original method is not applicable. So for the Stirling number of the second kind, we can have a placing ball module if we have n number of distinct balls to put them in m number of identical boxes. But there is another requirement that the box cannot be empty. And we just mentioned that 4 kinds of balls, red, yellow, blue, and white balls, are to be placed in 2 identical boxes. In fact, through the enumeration, we can find it has 7 different ways of doing so. According to the concept of the Stirling numbers of second kind, which is a number of ways, we can take 4 elements and divide them into 2 groups, denoted with S42 should be equal to 7. Let's analyze a few relatively simple examples. For example, I want to put n number of balls into 0 boxes. How many ways can we do that? In fact, we can analyze that it equals to 0. And if I want to put n number of balls into 1 box, it will have only one solution. If I want to put the n number of balls into n number of boxes, and because in the Stirling numbers of second kind there are no empty boxes, that is why we put n number of balls into n number of boxes. Here there is only one solution. So let's analyze below. But what about Sn2? Sn2 represent n number of distinct balls to be placed in 2 identical boxes, and neither box is empty. How many ways can we put them? So in the Stirling number of second kind, the difficulty is that boxes look the same. Does it mean that in our first step we should first differentiate the boxes? For example, I take out the first element, and this time since we are going to put an element into 2 boxes, then let's name the first ball B1. This time the 2 boxes can be classified as one with B1 and the other boxes without B1. By doing so, both boxes are already distinct. Then for the other n- elements, we'll have only 2 choices. One is we should add in 2 boxes with B1. Another is to put it in a box without B1. So how many solutions will be? There are 2 choices for each ball, and there are a total of n-1 balls. Therefore, the total number of ways will be 2 to the power of n-1. But there is a clever part here, because in the Stirling numbers of the second kind, an empty box is not allowed. So we can directly remove the scheme with the empty box. Well, at this point we need to sum up so that the Sn2 equals 2. It is directly equivalent to 2 to the power of n-1. Everything we analyzed just now is the simplest form. Well, here we will think if it is possible to have recurrence relation. Since it was placing ball module, we can absolutely analyze a recurrence relation. For example, we just pick up one ball B1. If B1 is classified with different situations, B1 itself can possibly occupy the whole box. If it took the whole space in a box, then for the rest, there are n-1 boxes remaining with n-1 balls. So corresponding to B1 take us one box. So for the rest, there should be Sn-1, n-1 with solutions. If the box doesn't exclusively contain B1, then after B1 there will be n-1 balls that could be placed in m boxes, and B1 has m choices in first place. So if the box is not exclusive for B1, then the number of ways should be m times Sn-1 m. These 2 parts have no repetition and no omission. All the Stirling numbers of second kind in this model are covered. Therefore, we have this recurrence relation Snm is equal to Sn-1 m-1 plus m times Sn-1 m. So we just experimented with 4 balls to be put into boxes. The number of ways is 7. So S42 is equal to 7. Well, let's complicate the question a little bit. This time, not only do we have the 4 ball, but we already add a green ball to this question. This time we have 5 balls that we want to place them into 2 identical boxes with no empty boxes allowed. Then we can use the recurrence relation so that what should S52 equals to? According to recurrence relation, S52 is equal to 2 times S42 plus S41. We can analyze using the choices for the green ball. Is the green ball sitting alone in one box, or does it share the boxes with others? We already solved the S242, so we know S41 is 1. Then we can directly calculate S52 is 2 multiplied by 7 plus 1, which is 15. So we can see this recurrence relation is based on the different selection of boxes for the green ball. Using this, we got a very simple method. So is it really a direct expression for this? In fact, we see that in Stirling numbers of the second kind, it requires n distinct balls to be placed in m identical boxes with no empty box. This time for us, identical is not a very good thing, so we just think whether we could differentiate the identical boxes. We first transform the problem into n balls with markings to be placed into m distinct boxes with no empty box. So the number of ways is equal to the labeling member m factorial times S and M. It is equivalent to picking n elements from m distinct elements with repetition to compose an ordered permutation. Since it is a permutation, we should use exponential generating function. For the case of each box, currently there are either no elements, or have 1 or 2 or 3 or 4 elements, but there is a requirement of no empty boxes being allowed. Therefore, in our exponential generating function, x to the power of 0 is not allowed to appear. So we can write the generating function as x plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and there are m elements in total. So this generating function should be raised to the power of m. The expression inside is actual equivalent to e to the x minus 1. So the exponential generating function becomes e to the x minus 1 raised to m. We put this expression through the binomial theorem and expand it. Assume h is a variable that goes from 0 to m. It is cmh multiplied by minus 1 raised to the h's power, e to the m minus hx. So we find that the combination and the minus 1 raised to h are not a big problem. And the remaining e to the m minus hx, what does this equal to? E to the m minus hx actually use the expansion of ex. This can be transformed into 1 minus m minus h divided by 1 factorial x plus m minus x squared divided by 2 factorial x squared. Therefore, corresponding to the general term x to the k divided by k factorial, the coefficient in front should be equal to m minus h raised to k. Finally, we write it out as n goes from 0 to infinity, m minus h raised to n divided by n factorial, then multiplied by x to the n. The formula finally also need to add the cmh negative 1 raised to x multiplied together. After the chain multiplication, we can take out the corresponding h. N goes from 0 to infinity, n factorial times x raised to n. H changes from 0 to m. This becomes cmh minus 1 raised to h multiplied by m minus h raised to n. So we can find out the coefficient of the corresponding generating function. Its coefficient is sigma h from 0 to m, cmh minus 1 raised to h times mi minus h raised to m. This coefficient is exactly the number of scheme m factorial times s nm. So we can figure out the corresponding expression for the Stirling number of the second kind S and M is equal to 1 divided by the m factorial multiplied by sigma h from 0 to m cmh minus 1 raised to h times m minus h raised to n. So here we find the corresponding to Stirling number of second kind, we can directly have the expression of the general term. We don't need to use the recurrence relation to solve, but not all the nonlinear constant coefficients recurrence relation will have this kind of expression. Therefore, we can say that generating function can solve a great many recurrence relation, but it is not applicable to all of them.